In the last video, we saw that you could take something like a plus b to the third power, and you could expand it in a predictable way. The variables follow this predictable pattern, where the 3 becomes the exponent of the a, and then in the next term it goes down by 1, and then down by another 1 until there is no a. Whereas the b goes backwards. It starts off with no b's, b to the 0 power, and in the next term it goes up by 1, and then up by 1 again, and then up by 1 again. Now this isn't the answer yet because there are coefficients, and those coefficients can come from two possible places. One place they can come is from Pascal's triangle. You locate the row of Pascal's triangle that has this 3 as the second number, and those four numbers, 1, 3, 3, 1, will be the coefficients. The other place that you could get these numbers is by doing combinations, where the four numbers are 3C3, sorry, I have to go in the opposite direction, 3C0, 3C1, 3C2, and 3C3, where the 3 is the exponent that you're raising the binomial to, and the 0 is the power on the b. So in this case there is no b, so it's b to the 0. But you can definitely see that this 1 is also over here. Now, looking at these first three terms, I just want to examine for a second 3C0, 3C1, 3C2, and 3C3. In general, anything C0 is 1, so I'm just going to write n C0 is always equal to 1. And 3C1 is equal to 3 in general, and C1 is equal to n. But it gets a little more confusing here with 3C2, which is also 3, but it's a little more complicated. For NC2, the formula, when I simplify it, is n times n minus 1 over 2. And 3C3 is 1, but the general formula for NC3 is n. Then you go down by 1, then you go down by 2, and in the denominator you don't put 3, but you put 3 factorial. And these 4 facts are going to come in handy. A kind of unusual thing you can do with binomial expansion is calculate things out. For instance, in this case, 4 plus 1 to the third. Well, we know that's the same thing as 5 to the third, which is 125. By order of operations, you do the parentheses first. But what if instead, I didn't want to do it that way. What if instead I did a binomial expansion? Well, it would look like this: 4 to the third plus 4 squared times 1 plus 4 times 1 squared. And the coefficients would be 1, 3, 3, 1, which would become 64 plus 48 plus 12. Whoops, That should be 1 to the third plus 1, which would again turn into 125. Now this might seem like a necessary way to do that, but it would work. Isaac Newton came up with an idea, which is that you could use binomial expansion even if the exponent is some kind of a fraction. So let's first, I'm just going to call this n for now. Let's just look at what the first 4 terms of this expansion are. It's a to the n, b to the 0. I'm going to leave off the coefficients for now. A to the n minus 1, b to the first, a to the n minus 2, b to the second. I'll just go one more term. Just say dot, dot, dot. If there's an n here, if n's an integer, there would be n plus 1 terms. The coefficients are 1, nc1 is n, nc2 is n times n minus 1 over 2, and nc3 is n times n minus 1 times n minus 2 over 6. And you could plug in any integer for n and get the first 4 terms of the expansion. But what if I were to put a fraction for n? For instance, 1/2. Well, following, this n value comes up in these various places. Let's just see what happens. I would get 1a to the 1/2. I'm going to leave off the b to the 0. Plus n, which is 1/2 in this case. A to the n minus 1 would be 1/2 minus 1, which is negative 1/2. B to the first. Now this expression is a little complicated, n times n minus 1 over 2. So that would be 1/2 times negative 1/2, which is negative 1/4, over 2, which is negative 1/8. You subtract 1 from the exponent to the negative 3 over 2. And for the last term, it would be 1/2 times negative 1/2, which is negative 1/4. Actually, I'm going to do this on the side just to... n minus 2 is negative 3 over 2, and that whole thing's over 6. That would turn into negative 3/8. Positive 3/8 over 6, which is 3 over 48, which is 1 over 16. And that's the 4th coefficient. And it's going to go, I left off b squared here. And this should be a to the minus 5 over 2, b to the third. Now when n is an integer, this thing ends when b becomes n and a. The exponent on the b becomes n, and the exponent on the a becomes 0. But when there's a fraction here, it just goes on forever. I'll say plus dot dot dot. So we're not going to be able to get an exact answer, but this is the expansion for a plus b, at least the first 4 terms of the expansion of a plus b to the 1/2 power. Now let's see how we can use this to get a new square root algorithm. So earlier in this course we did a bunch of different square root algorithms. I think we did 4 of them. Now we have a 5th one. Let's say I want the square root of 11, which is the same thing as saying 11 to the 1/2 power. Well, I'm going to rewrite 11. I could write it as 10 plus 1. I could write it as 9 plus 2, 8 plus 3. I'm going to purposely write it as 9 plus 2, which is going to be better than 10 plus 1. We want this 9 to be a perfect square, so that first number needs to be a perfect square. Here's why. The formula from here of a plus b to the 1/2 is a to the 1/2, 1a to the 1/2, plus 1/2 a to the minus 1/2 times b. The third coefficient ended up becoming negative 1/8. A to the minus 3/2 times b squared. And the last coefficient is going to be positive, or the fourth coefficient is going to be plus 1 over 16, 9 to the minus 5 over 2 times 2 to the third power. So we're just going to do 4 terms of the expansion. Let's see what happens. 9 to the 1/2 is the same thing as the square root of 9, which is 3. 9 to the negative 1/2, just a little reminder that a to the minus x is 1 over a to the x. So 9 to the minus 1/2 is 1 over square root of 9, which is 1/3. Uh, 9 to the minus 3/2 is 1 over 9 to the 3/2. But a reminder, the way you take 9 to the 3/2 is you do the radical sign, you put the 2 down here and the 3 over here. So 9 to the 3/2 is square root of 9 to the third, which is 27. So this becomes 1 over 27. 2 squared is 4. And because 9 to the 5/2 is the square root of 9 to the 5th power, which is 3 to the 5th power, which is 243. This fourth term becomes 1 over 16 times 1 over 243 times 8. Now it keeps going forever. And we should expect that because square root of 11 is an irrational number. But let's clean this up a little. It becomes 3. This term becomes 1/3. This becomes minus 1 over 54. And this 8 cancels out with the 16. And it becomes plus 1 over 486, which is 1612 over 486. And that's about 3.31 something, or 3.32. Put it into a calculator and square it. And you'll get 11.002. And that's how you can take the square root with generalized binomial expansion.